Namaste and a very good evening to all of you. I welcome you to my channel, The Outlier. My name is Mithun. In today's video, I'll be talking about a very interesting technique which is called as PCA or Principal Component Analysis. I'll be using the Orange software to run a PCA model. Even before I execute the PCA using the Orange software, may I request you to subscribe to my channel, also like and share my videos. Let me begin by introducing the dataset to you. I've got 6 variables in the dataset. The first variable is the ID. By the way, this dataset is called as the iris dataset. This is a very popular dataset. There are different flower characteristics that is given, like sepal length, which is measured in centimeters, sepal width, petal length, petal width. These are the 4 input variables that we can use. The last variable here refers to the species of flower. There are 3 different species of flower. Let me click on the drop-down menu. I'm going to first apply a filter and then click on the drop-down menu. You can see here the names of the 3 species of flowers, namely setosa, versicolor, and virginica. I will now show you the sample size in this particular data set. Let me go to the last record. It says 150, which means that the sample size in this data set is 150. Remember, to perform PCA, we need a healthy sample size. With this introduction, let me now proceed to show you the interface of Orange. This is the interface of Orange. And using this interface of Orange, we will be running a PCA model. What is the first step to run a model? The first thing that I'll do here is to load the data set from the spreadsheet. To load any data set, you can simply right-click and type File. The very first option here is File. I'm going to click on the File option. You can see here the widget appears in the canvas. To open up this particular widget, you have to double-click. Once you double-click, make sure that under the File property, the path is set as Iris dataset. What Orange does is it displays the description of the dataset. It says Iris flower dataset is a classical dataset with 150 instances of setosa, virginica, and versicolor. 150 instances are there. There are 4 features with no missing values. That's a very important point. Further, you can see the names of the columns: sepal length, sepal width, petal length, and petal width. The variable type is also displayed. The first 4 variables are numeric in nature, and their rule would be it is feature. What I will do now is, let me just study this. This is a numeric variable. I'm happy with the properties here. So I'll just go ahead and apply the properties of the variables on each and every field. I have clicked on apply and I'll close this particular window. So far, what I have done is I have loaded the data set into Orange. What is the next step? The next step is to display the contents of the file. I'm going to right click and say data table. You can see here, this is the option of data table. We can establish a connection between the file widget and the data table widget. I'm now going to double click on the data table widget. Once you double click on the widget, you can see here, there are different fields. Each field corresponds to the different flower attribute. You also have the names of the flower. If you want to visualize this, you can choose the second item, visualize numeric values. In the cell, you can see there's a bar that is appearing. Longer the bar, larger the value. Smaller the bar, shorter is the value. Let me remove visualize numeric values and close this particular window. At this stage, we have loaded the file. We have also displayed the contents of the file. What is the next step? The next step is to perform EDA or exploratory data analysis. In exploratory data analysis, we will be studying the correlation between the variables which we will be using for PCA. Let me right-click and simply say correlation. In this option, I'll be feeding the input variables from the file widget. Let me go ahead and double-click on the correlation widget. What this displays is the correlation value between each pair of variables. For example, when you look at the first row, it says petal length and petal width. For this pair of variables, the correlation value is 0.96. So there is a very strong positive relationship between the petal characteristics. Secondly, when you look at petal length and sepal length, the correlation value is 0.87. Remember, any value which is greater than 0.7 indicates a strong positive relationship. So the second pair of variables, that is petal length as well as sepal length, again have a very strong positive relationship. Thirdly, we have petal width and sepal length. The correlation value here is 0.81, which is again greater than 0.7. Since the first three pair of variables, all of them have a very high value of correlation, we can go ahead and conclude that there is strong correlation between some of the variables in the data set. If you look at the next three pair of variables, particularly for petal length and sepal width, the correlation value is very weak. It is less than 0.7, and therefore the correlation value is very weak. There is a weak negative correlation between each pair of variables. So what is the conclusion from this exercise? From this exercise, we can conclude that there is strong correlation between some of the variables, and therefore we can go ahead with PCA. If you do not have strong correlation, if you have very, very weak correlation in the input data, it is advisable that you do not use PCA as a technique. PCA expects correlated predictors. If we close this particular technique, so far we have performed the correlation metrics and we have seen what is the level of relationship between each pair of variables. Now I will proceed to the next step. The next step would be to call the PCA widget. Let me select the PCA widget and establish a connection between the source node and the PCA node. I'll take a moment to explain what exactly PCA does. The first point when we are talking about PCA is that it's an unsupervised learning technique. I repeat, this is an unsupervised learning technique, which means that we don't have a dependent variable here. Secondly, PCA is often referred to as the dimension reduction technique. If you have 100 plus variables in the data set, studying 100 plus variables becomes very, very difficult. So using the PCA, these 100 plus variables can be reduced to just 3 or 4 dimensions. Studying 3 or 4 variables would always be a lot easier than studying 100 plus variables. That's why PCA is referred to as a dimension reduction technique. Nextly, PCA accepts correlated variables, processes these correlated variables, and gives us new components. These new components are uncorrelated components. Lastly, PCA helps us reduce the complexity of the dataset. So these are some of the important properties of PCA. By now, Orange would have run the PCA technique. Let me open up this particular widget to show the contents of PCA. In the left-hand side, you can see components. Let me reduce it to 1. When you are extracting only one component, the one component that you have extracted explains 62% of the variance in the dataset, which is very high. If we increase it to 2, you can see here, 2 components explain 87% of the variance. So the first 2 components themselves explain 87% of the variance. Nextly, if I include the third component, the percentage of variance explained is 96. And when I include all the 4 components, the percentage of extracted variance is 97. Let me reduce the number of components. One question that pops up in mind is, what is the optimal number of components that we need to extract? 80% is a good cutoff. You can extract as many components which give 80% or more than 80% result. So in our case, 2 components are able to explain 87% of the variance, which is a very good sign. So for this video, I will be extracting a 2-component solution. To the right side, what you're seeing is popularly called as a Scree plot. You can see the y-axis, we have proportion of variance, and the right side, you see the principal components. There are 2 lines, one is climbing up and the other one is climbing down. The line which is climbing up is called as cumulative variance. The line which is climbing up represents cumulative variance. On the other hand, the line which is climbing down is giving me the component variance. Let's look at the first component. The first component individually is able to explain 62% of variance. When you look at the second component individually is able to explain 25% of the variance. Further, when you look at the third component, the percentage of variance that is explained is quite less. The subsequent components go on explaining a lesser and lesser percentage of variance. This is how you interpret the line which is climbing down. This line which is climbing down is giving me the variance for each individual component. Let's now take a look at the line which is going up. We have already discussed that the first component is explaining 62% of the variance. If you look at the second component, if you look at the first 2 components together, they are able to explain 87% of the variance. 80% can be used as a thumb rule. If the first 2 components are explaining 80% or above 80%, you can stop there and say the 2-component solution would be appropriate here. I will choose a 2-component solution and close this particular window. So at this stage, what we have done is we have executed the PCA model and we have extracted 2 components. These 2 components can be used for advanced analysis as well. What next? We would like to check the distribution of these 2 components. When we did correlation, that is called as EDA, or sometimes people call this as pre-processing. We have now built a PCA model. Whatever we are doing after building a model is called as post-processing. As part of the post-processing activity, I would like to look at the distribution of the 2 components. Let me first check the scores. To check the scores, let me right-click and say Data Table. Let me now establish a connection between PCA and the data table. Now you can see here, this is the data set that is displayed. The first component, that is PC1 or principal component 1, you can see here orange displays the percentage of variance that it explains 62%, and this is the new variable that we have created. The second component, that is PC2, is able to explain 25% of the variance in the data set. So since we have selected 2, what orange does is it creates 2 new fields in the data set. So for further analysis, we don't need to use the original variables, that is the sepal characteristics and the petal characteristics. For further analysis, we can go ahead and use only these 2 components. If we now close this particular window, The first thing that I'd like to do as part of post-processing is to examine the distribution of the principal component 1 and the principal component number 2. Let me quickly construct a box plot here. Right click and say box plot. Orange highlights the option for a box plot. And we establish a connection from PCA to a box plot. You can see here, to the left side, you have different variables. I'll begin by selecting PC1. To the right side, you are able to see 3 different box plot. The first box plot is for setosa flowers. The second box plot is for versicolor, and the third box plot represents virginica. My apologies. So each of these 3 box plots represents 3 species of flowers. What's very, very interesting here is the setosa flowers have a very small average value for the first principal component. You may ask me, what is the average value? The average value for setosa flowers is minus 2.7 for the first principal component. Let's go to the other extreme. You can see here the average value for virginica flowers would be 2.14 on the first principal component. So setosa has a very low value for the first principal component. Virginica has a very high score for the first principal component. Let me now select PC2. So this is the second principal component. We can check the distribution of the second principal component for the 3 species of flowers. Here we see an interesting trend, that is, for the second component, this is the box plot for virginica. Its average value is minus 1.17, indicating that there is a very low average score for the second principal component for the virginica flowers. At the other extreme, you have versicolor. Versicolor tends to have a high score for the second principal component. So we are able to differentiate the different species of flowers using only the principal component scores. I'll close this particular window. And as a last step, what I'd like to do is construct a scatter plot to show the distribution of the 2 components. Let me right click and type scatter. Here you have the scatter plot. I'm going to establish a connection between principal component and scatter plot. Open up scatter plot. You can see here the distribution of the first principal component along the x-axis and the second principal component along the y-axis. You can change the axis if you want. Axis x refers to PC1 and axis y represents PC2. When you look at the distribution of the principal component scores, you can clearly see here the blue colored circles represent setosa. And we saw that the setosa flowers have a very, very low value for the first principal component. The box plot clearly told us that the setosa species of flower has a very low value for the first principal component. When you look at the green color circles, they have a very high value on the x-axis. We already know that x-axis values represent principal component number 1. So the green color circles that you see represent the virginica species of flowers. So this again confirms what the box plot told us, that virginica species of flowers have a very high value for the first principal component. You can see here, this is the region which is dominated by the red color circles. And when you study the legend says that the red color circles here represent the versicolor species of flower. So the second principal component my apologies, for the versicolor flowers, the versicolor flowers have a very high value on PC2. So this is how we can use the different principal components to differentiate amongst the three species of flowers. With this, I have come to the end of today's video. In today's video, we have seen the different aspects of principal component analysis. We have seen the merits, we have seen the demerits of principal components. As part of pre-processing, we did correlation, and as part of post-processing, we did some visual representation like box plot and the scatter plot. With this, I have come to the end of today's presentation. Thank you very much for watching this particular video. Have a great day ahead. May I request you to subscribe to my channel, also like and share my videos.